Okay, let's get rolling. Let me get the chat and stuff up here. All right, so our homework for today is we're starting to build out this multi-user dungeon type thing. We created a little dungeon in the shape of a cross here, and ultimately the goal is that we're going to be putting our player into room 1 here, and then allowing our player to traverse through this dungeon. But for today, we were to build out we got ourselves started. Let's see, the official was build the exits and connect the rooms, make a room display itself so we can see that it's showing the correct exits and stuff. So it should display its title, its description, as well as the available exits. Okay, so let's go ahead and let's write that part first so we can test it on our initial pieces here. So initially we created our exit that goes from room 1 to room 2, and then another exit that goes from room 2 to room 1. And we added each of those exits to their respective rooms. So here in add exit, what are we doing? A room keeps track of a list of its exits. So these are all of the exits that exist inside of a room in the form of an exit object, one of these guys. All right, so we have a bunch of rooms. These are all the rooms in our dungeon. Then we create an instance of exit that leads from room 1 to room 2. So I've named it such that, you know, it reminds us it's going from room 1 to room 2. And then we're going to, so notice the destination of this exit is room 2. We're going to go ahead and add that exit to room 1. We're going to let room 1 add an exit to his list of exits, and it's going to be this particular exit. Similarly, for another instance of exit, I'm creating an exit right here. This guy has a destination of room 1, and the direction is to the south. We've named it room 2 to room 1. So we're going to add that exit to room 2. The exit we're adding is the one that leads back to room 1 to the south. All right, so that's our current setup. So let's go ahead and let's teach a room how to display itself. All right, so right now a room shows itself, it shows its title, and then it shows its description. So that'll be kind of like, you know, we are in the cave entrance, and then the description is the cave entrance. Well, now we want to show the list of exits for this room. So a lot of games would show something like obvious exits, something like that. Is what some dungeons, a room might have hidden exits, but for us we're going to say something like our obvious exits. And what we want to do is we want to build up a string that has our obvious exits in it. So the way a human being would perceive of our exits is not in terms of exit objects, but in terms of the, wasn't somebody supposed to remind me about fixing my scroll speed last time? But in terms of an exit's direction. So if a human being looks around the room, we want to see, oh, there's an exit to the south, there's an exit to the west, something like that. We just care about those words. Ultimately, we're going to translate those words into taking those actual exits. But for right now, what we want to do is we want to build up a string that is representative of our list of exits. So what I'm going to do is I'm going to create a string here called, we're going to call this guy exit string. We'll start it off as the empty string. We'll use concatenation to go through every element of our list of exits and concatenate onto exit string the direction of that exit. All right, so we're going to say for an exit in self.list of exits, do something, we're going to say exit string is equal to exit string concatenated with. We'll actually, we'll put a space at the end. So exit string concatenated with an exit dot direction. Is that what you call it in exit direction? Yep, direction is the name of the attribute. So an exit dot direction. And then we'll concatenate on a space there at the end. So for instance, if we have two exits in our list of exits, we have one to the south and one to the west, we would go through this loop twice. The first time we would concatenate south onto the empty string, and then our exit string would be called south, would contain south followed by a space. The next time through, we concatenate on west, so it would be south space, west space. So we'll have an extra space at the end, not the end of the world. And so that's what exit string will ultimately hold. And then what we'll do here is we'll put our placeholder and convert this guy to an F string. And our obvious exits will be inside of exit string. All right, so what are we doing right here? We are building up a visual string-based representation of the exits in our room, using the actual exit objects to describe to us their directions. So this guy is just the string. He doesn't actually link to real exit objects other than each word inside the string happens to correspond to a direction in our exits. But if we're displaying this to human beings are going to see, oh, obvious exits, south and then west, something like that as an example. All right, so that's what display will look like initially. And let's just go ahead and test that quickly on our two rooms we've added exits to. So we'll say r1.display. Oops. r2.display. And then we'll actually go ahead and show r3.display because that guy has no exits in it right now. So he should show no exits in his output. Oh, sorry. This should be lowercase r1 and r2. So here's a cave entrance. Cave entrance is the description. Obvious exits are to the north. And we're in a dark room. The description is dark room. Obvious exits to the south. So those are our room 1 and room 2. And then we have a dark room, obvious exits. There's no obvious exits. And it's because we haven't actually added any exits to that room yet. All right, so that's our display. And notice that we're displaying room 1 twice there. That's why it's popping up. All right, so we want to go ahead and create our other exits now for that guy. First of all, any questions about what we're doing here in display?
Yeah, I have a question.
Sure, go ahead.
When you're going through the loop, how does it know not to add, like, so it'll add south first, say, and then it'll add north, but how does it know not to add south again when you're going through that concatenation?
Because this loop here, let me write this loop a second time using indexing. So I'll say for I in range of 0 to length of self dot list of exits. Exit string is equal to, oh, let's steal this line. So these two loops do the identical thing. This guy makes an exit equal to each individual exit object once per loop through. So the first time it'll be the exit at bucket 0. The next time through it'll be the exit at bucket 1, then the exit at bucket 2. So we never come back and do exit 0. We don't go back to south because you know, in my verbal example, we have a list of exits that have two exits in it, a south and a west. So the first time through, this will be the exit that happens to have a direction to the south. The second time through, this will be an exit that happens to have a direction to the west. Then this loop will end. It's not going to go back and get to the south one again. This loop is the index version of that loop above. So if you don't like for each loops, if these guys don't quite make sense to you yet, we'll just use I to go through all the buckets of list of exits, bucket 0 through the last legal bucket in list of exits. So that's its length -1. Each time through, we'll concatenate onto our exit string the current exit we're looking at. That is the exit that lives at bucket I in self.listofexits. What I have highlighted there is an instance of the exit object. And I'm asking that particular instance to give me his direction. So these two loops are functionally equivalent. In this case, I'm using I to get me my particular index. This guy, and notice that I'm not using I for any other reason in here. So the only reason I'm using I is to get me a particular exit for my list. So in a situation like that, a for each loop like this maybe makes some more sense, because we don't actually need that value of I. We just want to do something for each exit that's in our list of exits. So does that make sense? Why? I mean, it'll do south the first time through, then it'll concatenate on the west the next time.
Yeah.
Then it's done.
Some people are thinking about it, if I think about it as an index.
All right, so that makes sense now?
Yeah.
All right, so that's our display method for an individual room. Now we want to go ahead and build out the rest of our exits. So we want to go back here and look at our picture. So we already have the exit going from room 1 to room 2 and back and forth. So now we want to go from room 2 to room 3 to the north. So we'll say exit R2, R3 is equal to an exit to the north that's going to lead to R3. And we'll say R2 dot add exit, exit R2, R3. So we created 2 exits here and added both of those exits to R2. So if we just want to view R2 right now, notice it shows us we have a dark room with description of dark room, and then the obvious exits are to the south as well as the north. Okay. Next is so we're done with all the exits for R2. So now let's focus on R3. R3 has an exit to the south, has an exit to the west, and has an exit, well, has an exit in all the directions. All right, so we'll go and build those guys. So we'll say an exit R3 to R2 is going to be an exit to the south leading to R2. Exit R3 to R4 to the west. An exit to the west leading to R4. Exit R3 to R5 to the east. Well, we'll just go north next. We'll just go around in the circle. So to R6 to the north. Guys to the north leading to R6. And then we have exit R3 to, I believe it's R5, but let's just confirm, to R5 to the east. All right, and then we want to, so these are the 4 exits that we need to now add to R3. So R3 dot add exit, this guy. R3 dot add exit. This guy. R3 dot add exit. This guy. R3 dot add exit. This guy. And then we'll go ahead and we'll show R3 dot display. And we see that we have a exit to the south, the west, the north, and the east for that particular room. All right, so we did R3 there and all those exits. Now we'll go ahead and do R4. He has an exit just to the east. So exit R4 to R3 is an exit to the east, R3. Say R4 dot add exit, this guy. And we'll go ahead and just display R4 real quick. So there's R4, has an exit to the east. Now let's do R6. He'll have an exit, actually let's do R5, so those guys are in order. So we'll do R5, he's gonna have an exit to the west leading to R3. So exit R5 to R3 is an exit to the west leading to R3. R5 dot add exit. That guy. Let's go ahead and print out R5. So there's our exit to the west from room 5. And then, last but not least, we'll do R6, an exit to the south to R3. Exit R6 to R3 is equal to an exit to the south leading to R3. R6 dot add exit. This guy. We'll go ahead and display R6. And there's our exit to the south. And this is our open cavern. That's our boss room. All right. So I think that completes the homework assignment. We've now linked all of our rooms up by exits. Now, so any questions about any of that?
I have one.
Go ahead.
If you look at line, I think it was 15. Yeah, question regarding scope.
Yep.
If direction was defined in the exit class, how does it know what direction is in the room class?
Because we are talking about this particular exit's direction. He doesn't know about direction directly. He knows about the direction from the exit class through this particular exit. This exit has a direction associated with it. You look at our exit class. Here's our exit class here. Exits know about their direction and they know about their destination. So it is not accessing this variable directly. So when you're asking the question about scope, line 15, this guy right here, this is not magically jumping into the exit class to get to this direction variable. Instead, it's accessing that direction variable through this instance of exit. And exit, so list of exits is a collection of stuff. This particular collection has a bunch of exits in it. How do we know? Because that's what our add exit function does. Add exit takes an exit as a parameter and it appends it to that list. All right, so this guy is an instance of the exit class. So this loop goes through every single instance of the exit class that lives inside of our list of exits. So each time through here, an exit is an object. It's an instance of the exit class. And exit objects have directions that are associated with them. So this guy is not, so to your point of it being scope, we are not magically accessing a variable that lives inside of exit directly. This guy is owned by an instance of the exit class. So we are getting him by asking the exit that we have access to, which we do have access to that guy in our local scope. We're asking that particular guy to tell us what direction does he lead. Does that make some sense?
Yeah, thank you.
Okay. Other questions? All right, now one thing, this will be a little foreshadowing because I want to get our player in there moving around, but we'll come back and make another pass at this later. I think we can all agree, first of all, if you just paid 50 bucks for this video game, you'd be kind of unhappy. Not a lot of rooms to explore, right? Okay, but, you know, so we had, what, a total of 6 rooms to work with here. This was pretty tedious, right? Going through and kind of connecting all of our Legos to each other. You know, not the end of the world. It was good practice creating our instances of objects and things like that. But there's probably a better way. I'm going to go ahead and represent it in our notes, but we're not going to look at it quite yet. But if I kind of come down here, we're going to talk about data representation languages quickly. So I'm going to say it would be nice if we could describe our dungeon in some convenient text-based way and then process that text to automatically generate our dungeon and all of the exits. So it would be nice for us to be able to sit here and create this 700 room dungeon, right? And have that translate into this text document that's in a very specific format, let's say. And then have our Python program go through and process that document and automatically do all this junk. Creating exits, adding exits, all that stuff, because we don't care about these variable names. This exit R4_R3, we're never going to use that again. We only did that and wrote it with a very specific variable name to maintain our sanity so that when we went to, we knew who we were going to add it to and we knew where it was going. So that when we went and added it to that guy and led to this guy, where's my room 4? Oh, when we added it to our R4, we knew which guy to add to it. So this is pretty tedious, and we were able to kind of hold it together for such a small little dungeon, but we can imagine this becoming pretty mind-numbing pretty quickly and pretty error-prone pretty quickly, right? So with that in mind, I'm just going to introduce the words here. We're going to come back and make a pass at this, but you've probably heard of these things before. So there exists some languages for representing data. Historically, we had something called CSV. These are comma separated values, and these are still used today, actually. You can like use Excel and you can export a spreadsheet using CSV so that it can then be regenerated someplace else or processed someplace else. So this would be pretty old. Then for most of you have probably seen that phrase before, XML, that word before. This stands for extensible markup language. So we'll just say for right now, this looks like HTML. So it's a tag-based language that describes meaning. Yeah, let's just leave it at that for right now. All right, so if I went to a web page, let's just open up this guy. Yeah, so here's Google's web page, and I right click on this guy and I say view page source. There's some other stuff in here, but do you notice here, like, that's a tag for head, and there's a closing head tag right down here. So everything in between these two tags represents the header for this web page. And then here's an opening link tag, here's the closing link, so on and so forth. So these tags, this data representation language, describes what these various things in here mean. All right, but even with that in mind, we would say XML is pretty verbose. I mean, this is Google's webpage, and there's quite a bit of stuff there. And when you really think about it, most of that stuff is the tags themselves. The actual data that we're marking up isn't that much. So XML is still used today for a lot of different things. It was a chicken or the egg thing. So HTML came first. Then somebody said, you know what? That representation language they use for describing web pages could work for describing other things. Maybe describing exits in a dungeon or rooms in a dungeon, things like that. So what they did is they created a way of generating a language that looks like HTML, but to describe other things. They called it XML. And you can actually define HTML using XML. In fact, if you've noticed some of your web browser, if you've gone and searched for it, it has a mode that you can turn on. You can say enable XHTML mode. And then what that does is it makes your browser break on about a third of the web pages. And the reason for that is HTML being so old, you had the early web browsers not necessarily all agreeing on what was properly written HTML. So that's why if you're a web developer today, you have to test your web pages on the three popular browsers, let's say, to make sure it looks reasonable on all three, because it doesn't always look identical on all three browsers. So like if you're trying to use Blackboard or something like that, and you're having issues, a lot of times the first thing somebody asks you is, oh, what browser are you using? Maybe try Chrome or maybe try Firefox or something like that, because maybe it'll behave a little different on a different browser. So HTML is kind of, even though it has a formal definition of what's proper formatted HTML, our browsers have kind of become bastardized to the point where they no longer adhere to that strictly. They'll kind of allow some wiggle room in the HTML language, where XML defines perfect representation of code. So if you are adhering to XHTML, which means the HTML language described using XML, which requires it to be complete, and you tell your browser to adhere to that, you're going to have some web pages break because they're not necessarily adhering to proper HTML. But for purposes of our discussion here, XML would be a representation of a data representation language, not to be confused with a programming language. So programming languages are, they have a way of representing memory, asking questions, and repetition. HTML is so I'll even add it here. This is hypertext markup language. So this guy describes web pages. So this guy does not allow you to create variables. He does not allow you to create loops. He does not allow you to ask questions. He's not a programming language. That doesn't mean he's a waste of time. He's a data representation language. His job is to describe the stuff so that a web browser can make your web page look pretty. So XML was born out of HTML. Now, probably the common way, the current way of representing our things, and you've actually seen this already accidentally, is something called JSON. This is JavaScript object notation. So a programming language called JavaScript, it represents its objects, like we're writing objects right now in Python. So we're creating exit objects, room objects, player objects, JavaScript object notation is how JavaScript represents its objects. And this guy looks like dictionaries in Python. So we've seen that curly brace name value pair type thing inside of Python for describing things. In fact, we actually went through that process when we were looking at, like, oh, well, if we were representing fractions, we could represent a fraction as a dictionary with a numerator and a denominator, but we have that weakness where it doesn't know how to perform things. It doesn't know how to perform things outside of just keeping track of data. Well, that's okay with us, because if I look back at my objects here, let's just look at room that has the most stuff in it. These three functions will operate on any attributes that we pass in. We don't need that stuff to be stored for each individual object. We just need that stuff to be blueprinted one time. You know, this is what the constructor looks like. This is what the display looks like. This is what add exit looks like. But then each individual room we create will have its own attributes we create. All right, so we only need, if you're building a bunch of houses in a neighborhood, you only need one blueprint, and you build 5 houses, but you put different stuff in each of those houses. But they're the same house. They have the same room size, the same number of bathrooms, all that stuff. So you need one blueprint, but you'll have a way of describing the contents of the 5 different houses, and those would be unique to each other. All right, so JSON is a way that we can accomplish that. All right, so moving down the line a little bit, we might decide that we can actually describe our dungeon maybe using something like JSON, where we describe our rooms in there, we describe the relationship between the rooms in terms of exits, and then we write some code that maybe looks a little complex, but it will take any JSON representation for a dungeon and turn it into all of the room and exit objects required and link them up. All right, so we do the hardship once, and then in the end, we get you know, the ability to have a dungeon with 5,000 rooms in it and it not make us go nuts. All right, now you might say, okay, well then on the other side, if I'm describing my dungeon using JSON, well, that's going to be tedious. Well, then we have another computer program we might write that has the ability to, you know, click a little plus button, create a new room, and name that room, and it generates the JSON for us behind the scenes. So we have a program that allows us to drag and drop our dungeon rooms, which generates JSON, and then we have our program here, which takes in JSON and generates our dungeon. So that's human beings making our life easier by using programming to build our tools. All right, but for us right now, we're gonna say that we were able to conceive upon our dungeon by just kind of rigging it together. This is our initial prototype, so we were able to deal with this. So we're not gonna bring in those data representation languages yet, but recognize that they do exist and we could use them for this type of thing. All right, so now we have our dungeon. Well, we want to now be able to explore this dungeon. So I'm going to go ahead and I'm going to create a player. The player is equal to player, and a player takes in what parameters? A name, an well, it was just something on my laptop screen. So it takes in a first name, a last name, an age, and a jersey number. All right, so he's going to take in, first name is Mr. Of course, Mr. Gonzalez is a dungeon crawler. Mr. Gonzalez, I wonder how old he is. I think he's like 5. And his jersey number, it's probably 0. All right, so there's Mr. Gonzalez in our game. So we've represented a player down, but now we want to be able to add a player to a room. Okay, Because if we go back here, let's draw our picture. Here, I'll copy this just so we have it in the right order. So now we're back here. Now I just created our player. Let's make the player green. Well, Mr. Gonzalez does wear a lot of red. All right, so this is our variable called the player now that we've created. All right, so he exists here. Our dungeon exists here. We want to start off by getting our player into room 1 of our dungeon. Now remember that dungeons, if I just represent a particular room here, this guy has, do we call it a title or do we call it a name? What do we call it in room? Yeah, we call it a title and a description, okay? So this guy here is gonna have a title. He's gonna have a description. He's gonna have a list of exits, and he's gonna have a list of inhabitants. All right, so these are the things that are associated with each of our rooms. So we know this room is what we called it a cave entrance, and then we called it the cave entrance. He has, in our list of exits, he has a single exit to the north that leads to room 2. And right now his list of inhabitants is empty. What we want to do is we want to get Mr. Gonzalez added to room 1's list of inhabitants. Okay, so we'll go back to room. And just like we have an add exit, we're going to have, and I'm going to actually define this specifically as define add player, because we're going to end up treating players a little bit different than other inhabitants. Eventually, we're going to have little, I don't know, bunnies or something hopping around in our dungeon, and those guys will be a little bit different than a player, in that they won't have necessarily humans controlling them, but they might still move around the world themselves. All right, so add player is going to take a player as a parameter, and he's going to add that player to this room. So we're going to say self dot list of inhabitants dot append, and we're going to append a player to that list of inhabitants. Okay. Now for players, well, we'll come back to that part in a second here. So now a room also is going to have a list of inhabitants. So now we probably want to show, for displaying a room, not just the obvious exits, but also who else is there. So maybe we do that before our exit string, and we do a similar thing. So we say inhabitants string starts off as the empty string, and we're going to go through all of our inhabitants. So we'll say for, right now we're going to call it for a player. We'll say that's good, because I'm going to close some gaps here later on. For right now, we're calling them inhabitants, even though the only inhabitants in our world are players. We're eventually going to have other kinds of inhabitants. So for an inhabitant in self dot list of inhabitants. Did I spell it right? Probably. We'll say inhabitant string is equal to inhabitant string concatenated with an inhabitant, and we want to get this person's, maybe do we want to just list the inhabitants by their first name? Instead of having this big long string of things. So, it'll be, well, actually that would look kind of funny. Also here, just Mr. We'll do the whole name. So we'll add to our inhabitant string an inhabitant dot first name, concatenated with a space, concatenated with an inhabitant dot lname. And then we'll give it an extra space at the end. All right, so we can write it that way. Or we can teach inhabitants, so teach our players, how to give us just their name. So def get full name. And this guy can return self.fname concatenated with a space, concatenated with self.lname. So now we can ask a particular player to give us his full name. So he'll do that concatenation inside there for us. So then inside of room here, we can say, get full name from our inhabitant. That's what I called it, right? Get full name. So we'll build up our inhabitant string with whatever it currently is, concatenated with the full name of our inhabitant, concatenated with a space. And then we'll have we'll do that for all the inhabitants in the room. And then we'll say something like print also here. And we'll put our inhabitant string in there. All right, so now we can display a room showing all the inhabitants in the room as well as all the exits that are in the room. Now, right now, I have not put, I've created my dungeon, I've created my player, but I have not ultimately put my player in room 1 yet. So if I run this right now and I say r1.display, it's going to show me what R1 looks like with an entrance to the north, but notice nobody is obviously there yet. Nobody else is also there yet. So now we want to add our player to room 1. So rooms have the ability to add a player to them, and it will add that player to the list of inhabitants. R1.add player, the player. And now when I run it, Mr. Gonzalez is in that room. All right, so he has finally made his way to the entrance of the dungeon. So he's now part of this list of inhabitants. So that is one of the things that list of inhabitants points to. Is Mr. Gonzalez. He currently lives at bucket 0 of list of inhabitants. Even though list of inhabitants might hold many inhabitants, right now it just holds 1. Okay, so now there we have our put together dungeon with a player dumped into the first room. So now what we want to do is we want to have the ability to allow the player to move around the dungeon. Now, to give you a jump start here, what we're going to do is for players, a player is also going to need to know about the current room they're in. So when we create a player, they're not in a room. When we first created Mr. Gonzalez, he's just out in the void. But we're going to go ahead and set a variable here called self current room, and we'll start it off as being equal to none. He is not in a room right now. But what I'm going to do is I'm going to have a function called set current room. that's going to take a room as a parameter and set this player's current room equal to the room that was passed in. So now a player can be notified that he's entered a certain room. And when do we get that? When a player is added to a room, we will add that player to that room's list of inhabitants, but we will also let that player know about the room he just entered. What room did he just enter? How does an object, he entered this room, right? The room that is calling their add player method. How does an object refer to itself from within itself? Using the keyword self. Inside of add player, which lives inside of room, we are trying to let this player know, a player, know that his current room is us, is this particular room. And the way that an object refers to itself from within itself, this room calls himself self. So he's going to pass himself into the current room for the player. The player will then set his current room to that room. So now, instead of saying r1.display, if I say the player dot current room dot display, this is show the room that the player is currently in. We see we still get the cave entrance. All right, this player was added to room 1. When he was added to room 1 then let the player know. This is room 1's add player as an example. He added the player to his list of inhabitants, and then room 1 said, player, set your current room to me. So in that particular case, self is room 1. Okay, so for your homework, I'll put it on a slide here. Ask the player over and over again what he wants to do. Support moves north, south, east, west, and your code should remove the player from the room they are currently in, add the player to the room in the direction they chose, display the new room. All right, so for your homework, you're going to have to figure out, how do I remove a player from the room? How do I get this player out of that room's list of inhabitants? And then you're going to have a way of asking the player using the input function over and over again, what would you like to do? The player says south, and there's an exit to the south. It'll remove the player from the current room, add him to the room to the south. They'll take that exit. All right, so when this is all said and done, your player should be able to walk all around the dungeon. Make sense? Okay, so I'll post this code up on Slack, and you should be able to, this will be due on, what's today, Friday? This will be due on Monday. All right, well, have a good weekend. Also, as a reminder, we do have next week's Tech Talk is on Wednesday. It's going to be in this classroom, so same link here. It's 6 p.m. on Wednesday the 7th via Zoom.